All right, welcome back. This video is about improper integrals, and what makes them improper for us is that they involve this infinity symbol. Every integral we've worked with so far has been proper. What made it proper is that the bounds of the integral were numbers, like 5 or 2 or pi or -8 or 0, and that the function that we're integrating doesn't have any weird stuff happening in between the bounds of integration. An example of a function that has weird stuff happening is the function 1 over x. At least if our bounds contain 0. So say we're integrating from -x to 2, the function 1 over x. That integral is improper because 1 over x does not exist at x is equal to 0, and x is equal to 0 is in between -2 and 2. So that's one case of an improper integral. Any function being integrated having a division by 0 in between the bounds. That case is not covered inside this course. We're not going to examine how to work with those types of integrals. That's held for a different course. But we will look at another type of improper integral. The type of improper integral that signals itself more clearly, where either the top bound or the bottom bound are plus infinity or minus infinity. So again, proper integrals are the type that we've already been doing. The integral involves numbers, or the definite integral involves nice numbers like 0, -8, pi, 2 on the top and the bottom bound. And the function doesn't have any weird pathological problems inside the region of integration. So no divisions by 0, no explosions. And we're going to explore the extension of this idea of an integral to the case where the bounds are plus and or minus infinity. So there's one case where the integral goes from a to infinity. There's another case where the integral goes from minus infinity to b. And a third case where the integral goes from minus infinity to infinity. We'll explore all three of these cases. Infinity is dangerous and demands a proper treatment. Once in a while, I may forget that and treat it in a very cavalier kind of way. I'd ask you to limit your replication of my poor writing practices in dealing with these infinities. I'll try mostly to write it out formally. The way we're supposed to do it, like the formal, careful, rigorous way we're supposed to write an improper integral of the form integral from a to infinity, is we're supposed to write it as a limit. We're supposed to replace the infinity with a b, the letter b, and then put a limit as b approaches infinity in front. This splits our operation up into two steps. First, we take the integral from a to b of the function, and then we take a limit of the result. If this limit exists, so if a number comes out of this limiting process, then the language that we would use is we would say that this integral converges, and it converges to that number that comes out. However, if when we take the limit, the number does not exist, say we get infinity, or we get a division by 0, or we get some other problem, then we would say that the limit, or that the integral diverges. And I'll tell you what that means in terms of area with some examples. In a previous calculus course, you likely talked about limits to infinity, and we're going to revisit that. You may have discussed the formalism. What does it mean for x to go to infinity and the limit of f of x going to L? We're not going to get into the formalism. I'm just going to tell you what it means in plain language. The limit as x approaches infinity of f of x equals L means that the y value of the function will eventually approach L when x gets large. So if x is really big, then f of x is going to be really close to L. Slightly more formally, we could say that you can make f of x as close to L as you want by making x sufficiently large. It does not mean that f of infinity equals L. So I want to explore two different types of functions and their limits as x approaches infinity. And the way that we're going to explore that is by not plugging infinity in, but by plugging in progressively larger numbers into the function, and then looking at kind of the pattern. So I'll plug in, let's say, I'll plug in 10, I'll plug in 100, I'll plug in 1,000, and maybe that'll be enough. So what is f of 10? We're going to get 10 squared, which is 100. F of 100 is 100 squared, which is 10,000. 1,000 squared is going to be 1,000,000. As x gets larger and larger and larger, the output, or the y value, or f of x, gets even larger. So if we were to imagine plugging in infinity, what is f of infinity? What is the limit as x approaches infinity of f of x? Because we can't plug infinity in as if it was a number, because it's not a number. Is this going to be big or small? It's going to be really big. How big? Well, is it a billion? Is it a trillion? Is it a zillion? And it's as big as imaginable. Infinity is a difficult concept to understand fully and properly. Well, infinity plus 1 is infinity. You add 1 to infinity, it doesn't change. And infinity plus 1,000,000 is infinity, because that's just adding 1 1,000,000 times. Each time it doesn't change. So that's, I mean, it's quite unfriendly. It violates many of the properties of numbers because it's not a number. We would say that when the limit as x approaches infinity, x squared is infinity. It's infinitely large. If someone claims differently, if they claim it's actually a number, then they haven't plugged infinity into it. They haven't done the limit properly. However, the second example is more interesting. Something else happens. I'm going to choose the same values. Our function is 1 over x squared. I'm going to choose 10, 100, 1,000, and then look at the pattern. So here we have 1 over 10, which we put in the decimal form is 0.1. Or 1 over 10 squared, sorry, I forgot to square it. 1 over 10 squared, so it's 0.01. 1 over 100 squared, so that'll be 0.00. Let's see, I have to add 2 more zeros, right? So I shift it over by 1, 2, 3, or maybe that's too many. Okay, and then 1 over 1,000 squared. 0. How many zeros are we going to have? That many zeros, I think. So it's getting really small. When x gets big, 1 over x squared gets really small. So I put infinity, and you get 1 over infinity squared, which is very small. It's 0. So don't write this. Don't write infinity squared. Don't write 1 over infinity squared. This is bad. Bad notation. That's how you can understand how to take limits of these types of functions. Just imagine plugging in progressively larger numbers in for x and looking at the trend. Is it getting really big or is it getting really small? Is it eventually going to go to 0? Is it eventually going to go to infinity, or is it going to do something else? Here's some other types of limits. We can understand each of these in terms of a graph as well, or we can understand them in terms of their algebra. I'm going to do both. So e to the x. I'm going to graph e to the x. Quick sketch of e to the x. X, y equals e to the x has this shape. And as x goes to infinity from the graph, it keeps growing and growing and growing. So we are going to get infinity. But algebraically, if you want to understand what's happening without the graph, what does e squared mean? E squared means e times e times e. Or sorry, e squared means e times e. E multiplied by itself twice. What does e to the 100 mean? E multiplied by itself 100 times. So if you were to think of this as e to the infinity, which is e times e times e times e forever, this has to be infinite. If you think it's not infinite, if you think it's some number of billions or trillions, that's because you haven't stopped multiplying by infinity. E to the infinity means you're multiplying e by itself forever. You never stop. Longer than the age of the universe. Infinitely longer than the age of the universe. You just keep multiplying. The only thing that you can put down as an answer is infinity. However, what's happening if we plug in minus infinity? So that's e to the minus infinity. Or looking at the graph, that's moving to the left. Negative x values. Well, the y value of that graph is approaching 0. What's happening algebraically? E to the minus infinity, let's use exponent laws. We can write that as e to the infinity in the bottom. E to the positive infinity in the bottom, which is 1 over e times e times e dot 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 times e forever. Right? We keep multiplying forever. So 1 over infinity, which is, well, what is 1 over infinity? Let's think about a lottery. 1 in a million is low odds, right? 1 in a million odds of winning. 1 in a billion is worse. Right? It's lower odds. What are the odds of winning a lottery? Or how good are your odds of winning a lottery that has 1 in infinity odds of winning? Is that good odds or is that bad odds? It's really, really bad odds. It's worse than 1 in a billion. Worse than 1 in a trillion. It's 0 odds. You are not going to win that lottery. Now this stuff in the middle, we should not write that. We should not write those types of steps. I'm just going to put down the answers, 0 and infinity, and say do not write the purple. Do not write what is in purple. We're just supposed to say what the answer is. But it's very, when you're learning about this stuff, it's not satisfying just to quote the answer. I think it's more satisfying to think about what exponentiation means. Like, what is this operation that we're doing? To use exponent laws, to have some intermediate steps, and at least justify to ourselves that this is what's happening. Okay, so for the next one, we have e to the minus infinity, which is 1 over e to the positive infinity, which is 1 over infinity, which is 0. We're just supposed to say equals 0. How about the next one? We have e to the negative infinity, which is e to the positive infinity, which is infinity. We could also draw a graph of e to the negative x. E to the negative x is like the graph that's pictured here, but flipped left and right. It's mirrored left and right. So it's increasing as you go to the left and decreasing to 0 as you go to the right. But okay, how about these ones? So the first one, we have 3 over infinity odds of winning the lottery. So I like to think about the lottery example, 3 in a million odds versus 3 in a billion odds. Gets worse, right? 3 in infinity odds is even worse than that. It's 0 odds of winning. How about 3 over minus infinity? Well, we know our rule of fractions. If we have a negative number, if we have a negative sign on the bottom, we can move that up top. So minus 3 over infinity, that's negative 3 or negative 1 times 3 over infinity, which is negative 1 times 0, which is 0. We can think about that function as well. We could draw this graph of 1 over x, y. 1 over x looks like this. And look what happens as you go to the right. Oh. 1 over x goes to 0. That curve is going to approach y equals 0. As you go to the left, you're on the other piece of the piecewise, not piecewise, you're on the other piece of this function. And the y value is also approaching 0. It's approaching 0 from below. It's approaching 0 from over here. It's closer and closer and closer. But it is going to approach that y value of 0 as x goes to negative infinity. So that's why both of these limits, from positive and negative infinity, of 3 over x gives you 0. X cubed, well, that's limit x approaches infinity, so it's going to be infinity cubed, which is infinity times infinity times infinity, which has to be infinity. How about negative infinity cubed? So that's negative infinity times negative infinity times negative infinity. We have 3 negatives, so negative times negative times negative, so it'll be an overall negative infinity. And then we can do the exponential functions, 2 to the infinity, which is 2 times 2 times 2 dot 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 forever. Keep multiplying, keep doubling it, right? Keep multiplying by 2 forever. It's infinity. And then the next one, we have 2 to the minus infinity, which we can rewrite as 1 over 2 to the infinity. So 1 over 2 times 2 times 2, which is 1 over infinity, which is horrible odds of winning the lottery. 0 odds of winning, so 0. And then the last one, we could think about this as 1/2 to the infinity, which is 1/2 multiplied by itself forever. 1/2 times 1/2 dot 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 times 1/2 forever. So you keep cutting something in half. Get smaller and smaller and smaller. So maybe it's like a single atom. We haven't gone far enough. We have to cut it in half again. So it's half of an atom, and we cut that in half. We keep cutting in half and half and half, and like it doesn't stop. Trillions of years later, we still have to keep going. We still keep cutting it in half. The only sensible thing we can put down as a result of cutting something in half forever is nothing. It's 0. That's what it's driving towards. That's what the value of the limit is. That's its ultimate end point, if you could think of it that way. It's headed towards 0. It's headed towards nothingness. What about the next one? Negative infinity. So 1/2 to the negative infinity. Well, remember with our exponents, if you have a negative exponent applied to a fraction, we can change it to a positive exponent, 2 over 1, by flipping numerator and denominator. And then that's 2 to the infinity, which is infinity, 2 multiplied by itself forever. So what we're supposed to write is what's in blue. We're not supposed to show any steps. Don't write what's in purple. If you're going to write what's in purple somewhere, put it on a little scrap of paper, rough calculation paper, and then when you're done with it, go shred it, hide it, throw it away, burn it, because it's not proper math. The stuff that's written in purple here is, like, this is playing with fire. To write out arithmetic with infinities like this is irresponsible. But I like it. All right. I'm going to put down some graphs just to help you think about limits to infinity. So e to the x looks like this. 2 to the x looks similar. And limits to infinity, you can imagine taking a math car and pushing it to the right. So limit as x approaches infinity of b to the x is going to be infinity for b larger than 1. So math car is going to get a y value of infinity, whether you put it on the blue curve or the red curve. But if we put a math car over on the left-hand side, so I got red, I got blue, I'll use the orange, so I'll put it over here. It doesn't matter if I put it on the blue one or the red one. If I push it to the left, limit as x approaches minus infinity, b to the x is equal to 0 for b greater than 1. So that's how you would make sense of the limits using graphs for either e to the x or 2 to the x or 3 to the x or any function of that form. Now the next type, e to the negative x, is mirrored. It's flipped left and right. So I'll draw that over here. I'll use a different color red because I don't want to, I want to label things and be able to track what's what. And 1/2 to the x has the same shape. Has that shape. And we can imagine putting math cars on here. So there's my math car. I'm going to push it to the left. So limit as x approaches minus infinity of b to the x is infinity. And then if I take a math car, put it on the right, push it towards infinity, limit x approaches infinity of b to the x is equal to 0. And these are for zero less than b less than 1. So for values of a base that are between 0 and 1, this is what the behavior is. And it's based on either the algebra, like what was done here, using this as kind of a legal notation, or based on what does the graph do, what is the picture doing. And then for the last one here, the last picture I want to draw is what's going on for 1 over x, 1 over x squared. So 1 over x looks like this. For both of those pieces, and 1 over x squared is like this. So I'm not going to draw it properly, like I'm butchering the picture. I'm butchering even worse. 1 over x squared looks like this. And then you can take limits as x approaches infinity or minus infinity of each of those. And you'll see that it's 0 in both cases. So I'll summarize to say that the limit as x approaches infinity of 1 over x to the n equals 0. The limit as x approaches infinity or minus infinity of 1 over x to the n is also equal to 0 for n greater than 0. So you can use that as a theorem. It's most calculus textbooks, it's formally stated as a theorem of limits. And you probably saw this in your previous calculus course. So this is a type of review. But I think it's helpful to, again, see the graph and understand where the values of these limits are coming from. We'll continue with examples in the next video.